Welcome back to our course in stochastic processes. We now enter the last section of this course, which is all about Brownian motion. And today there will be a special chapter on the so-called quadratic variation. We already heard about this topic in discrete time martingales. And actually the same applies also to continuous time martingales. So we're looking for some kind of process such that martingale square minus this process is again a martingale. And we'll discover that the quadratic variation of a Brownian motion by time t is t. So let's see what that means. So, quadratic variation. But before we come to this topic, there's another topic here, Blumenthal's 0-1 law. We already encountered a 0-1 law, which was Kolmogorov's 0-1 law, which stated that the sigma algebra, which was also called T as here, of the so-called terminal events for a family of IID random variables, or of independent random variables, is p-trivial, which means if you take events which do not depend on any initial finite number of random variables, so only on xt, t bigger than s for all s, so that's the tail sigma algebra, then the probability of any event in this t here is either 0 or 1. And a similar thing holds true if the xt, so they're not independent, but they are Brownian motion. So xt is a Brownian motion here. And there are two sigma algebras we will consider. The sigma algebra near 0 and the terminal sigma algebra. And both of them are also p-trivial. But what is important here, we assume all filtrations here, we assume them to be complete. And that means that n, which is the set of null sets, is already part of F0. So let's quickly prove this. First, we already saw that the sigma, so the filtration generated by a Brownian motion. So Brownian motion is right continuous, so it's continuous, so it's also right continuous. So this sigma algebra is also right continuous. And that means F0 plus, well, that's this intersection here. It's right continuous, so that's sigma of x0, but it's starting in x. So the Brownian motion here starts in x with x0 is deterministic. And well, this sigma algebra is the most trivial thing. It only contains the n here. So it contains only null sets and complements of null sets. And that's, of course, a p-trivial thing. For the tail sigma algebra, there's a nice trick how to come to this conclusion. Maybe you remember that if xt is a Brownian motion, then also t times x index 1 over t is also a Brownian motion. And if t approaches 0 here, x1 divided by this small number, so the sigma algebra of this xt prime here will be the tail sigma algebra, because, well, we can look at this intersection here, sigma algebra of all xt's, t bigger than s, or s smaller than t, I have to say. No, xt, t bigger than s, so that's the tail sigma algebra we want to have. Well, that's this tail sigma algebra. Maybe I should use a prime here, because xt prime is exactly this thing here. But the sigma algebra doesn't care about the constant t here, but it cares about the 1 over t, because if t is less than or equal than s, then 1 over t is bigger than s. So, so like this here, no, there's something wrong. I have to use a prime here, but no prime here. And as we just saw, this sigma algebra, t less, so yeah, just use this equation here, but exchange s and t, and you exactly have this here. And we already saw that this thing here is p-trivial. So this thing here, which is the tail sigma algebra, is also p-trivial. Okay, that was a very small thing about Brownian motion. So you can now also already know the tail sigma algebra of Brownian motion is p-trivial. And now we come to the quadratic variation. First, we have to say what variation or quadratic variation is after all. And let me try to draw a picture here. And, well, I just used some curve. Now I'm using a rather smooth curve. So what is the variation? So maybe I should draw it a bit differently, I think. I should draw maybe at least something like this, okay. Let's say here's my t and the variation. So how do I come to a variation? I use intervals or steps t0, t1, and so on, tkn, which is the last thing here. And I can make this thing finer and finer and finer and finer. And in the nth step, at the nth thing of making this more and more refined, I'm calling this theta n here. I'm doing it like this, that the maximal difference between two time points goes to 0. And then the L variation of this function f here is defined like this. So, yeah, I'm using this difference in function values, absolute value, to the power of L, so that will be the L variation. I'm summing all this, and I let n go to infinity. And then, if that limit exists and is independent of my theta, so the series of partitions here, then I call this the L variation, and new LT of f. So, well, here let's just assume L equals 1, and in this figure here, because that's a simple thing. If L is equal 1, well, there is between here and here actually the function values decrease, and afterwards they increase. But when they decrease, as they do here, all what I'm doing here in the sum, I'm adding to the decrease of the function value until I hit the minimum. And afterwards it increases, and I just sum up all this increase here, which means, well, I could try to even draw the L equals 1 variation of this function. So I'm starting at 0. So from here on it's easy because it just follows the thing, and up to here I have to mirror this. So yeah, like this maybe. Yeah, like this. Like this. So when the function here decreases, the variation increases because of the absolute value here, and then it increases further. So that's the L equals 1 variation. So what else can we say about this variation? There are some very basic properties. So if I have a finite L variation, then the L plus 1 variation is 0. Okay. On the other hand, if the L plus 1 variation is bigger than 0, the L variation is infinity. Okay, I mean, that's basically the same thing as what we have here, because if this follows from this, the negation of this here follows from this, follows from the negation of this thing here. The negation of this here is bigger than 0. The negation of this here is equal to infinity. So this is really the same thing. So let's try to prove the first thing. So if the L variation is finite, then we have that the L plus 1 variation is 0. Oops. I need a black color here. Well, okay. So the L plus 1 variation, we have to argue it's 0. Fk from 1 to kn, absolute value f of t n k minus f of t n k minus 1 to the power of L plus 1, and I'm having a limit as n goes to infinity. So I have to argue that this here goes to 0, and the point is that I'm having the L plus 1 here, so I can use one exponent here and bound that from above by the supremum over all k, f of t n k minus f of t n k minus 1 times the same sum as before, but to the power of L. And this here is just the L variation, which is assumed to be finite. And this thing here, since the supremum of tnk minus tnk minus 1 goes to 0 by this assumption here, f is continuous, then also since f is uniformly continuous on the compact interval from 0 to t, so this supreme here also goes to 0, so we have something goes to 0 and is finite, so the limit must be 0. Okay, so that was important. That means, for example, so we saw here for this smooth curve here, the L equals 1 variation, so the 1 variation is finite, which means that the second variation, so L equals 2, the quadratic variation, is going to be 0. So that's a pretty smooth curve, which means we have a finite variation and a 0 quadratic variation. And for Brownian motion, what we have here, so x is a Brownian motion, and we then can compute the quadratic variation, so 2 means quadratic variation, and that goes to t. So that means it has a quadratic variation, and that means if L equals 1 here, that's positive, so the variation is infinite. So there are two things here to consider. The first is this here always holds as long as theta just converges somehow, then the quadratic variation here converges in L2. And if theta is ascending, which means, I define it here, that it's finer and finer, so I just add new times in the new partitions. And if it's this here, then the convergence is also almost surely. So we have two things to prove: L2 convergence and almost true convergence. For L2 convergence, that's just a calculation, and for almost true convergence, I just give the sketch of the proof. So proof of L2 convergence. So that's essentially only computing some moments. So let's start. What's the expectation of the variation when I did not let n go to infinity yet? Okay, I should write of x, but I ignore this and I just write this. And the expectation of the quadratic variation, so to speak. Well, that's just changing sum and expectation. Expectation of x t n k minus x t n k minus 1 square. And now the point is, this here, since x is Brownian motion, so the difference here has an n0 and time difference distribution, which means that the quadratic variation here is the sum k from 1 to kn tnk minus tnk minus 1. And of course, that's a telescope sum, which amounts to t. So the last tnk here is t, and the first one is 0. So that's the expectation. So let's also compute the variance. So the variance is then the expectation of nu 2 theta n minus t square. So that's the variance of nu 2 theta n, and nu 2 theta n here is this sum here, where f is Brownian motion. But since Brownian motion has independent increments, that's a sum of independent increments. And the variance of a sum of independent things equals the sum of the variances. So it's the sum of the variances. K from 1 to n. Variance of, well, x n, no, sorry, x t n k minus x t n k minus 1 square. So, well, what's the distribution of this thing here? So this thing here has the same distribution as tnk minus tnk minus 1 square root times z, where z has an n01 distribution. Well, yeah, so I'm taking the square of this thing here, which means I have okay, I'm writing down the sum, k from 1 to kn. I'm squaring this. So I'm going to the variance of this here without the square root. And when I pull this out of the square root, I have tnk minus tnk minus 1 square times, we have z square here. I have the variance of z square. Well, this here is something that's just a finite number, And well, this square, the sum of this square here, I can do the same trick as we already had. I can pull out one of these things. I get the supremum over all k, tnk minus tnk minus 1 times the sum tnk minus tnk minus 1. The supremum here, that goes to 0, and this here is t, because it's a telescope sum. So something which goes to 0 times something which converges to, which is t. That means as n goes to infinity, this here converges to 0. So we have shown the expectation is t, and the variance goes to 0. And that means we have L2 convergence, as we already claimed. For the almost sure convergence, that's actually a very nice proof, but I invite you to look that up in the manuscript, because it's a bit tricky. Here is an instance of a backward martingale. So, okay, how does all this come about? So, theta must be ascending, which means, well, I'm adding new time points to my partition here. So theta n minus 1 does not contain Tn, but theta n contains Tn. So if I'm here on the t-axis, here's my new thing Tn. That's only in my theta n, and all the others are in my theta n minus 1. And I have to closely look here. So when I think about what changes between the quadratic variation with n minus 1 here and with n here, the only thing which changes is around here. For n minus 1, I'm adding from the increment from here to here square, and for the nth step, I'm adding from here to here square plus from here to here square. That's the only difference. I argue here that I have a backward martingale. So as I write down here, so n is here, I write here minus n because n itself is negative, so that's a positive number. And let me try to convince you that that could be a backward martingale. So as in this figure here, let me say this here is my t. This one step before is my s, and that afterwards is my u. Sorry, not correct. That here is my r, and that's my u. And what I have here is not my t because t is already occupied, but I call this s here. Okay. And for the backward martingale, I'm considering, well, alpha is the increment between s and r, and beta is the increment from s to u. And I have alpha plus beta, which is the increment from r to u. That's what I have in the n minus, if I have the n minus 1 step. And on the other hand, in the nth step, I have here alpha square, so this increment square plus the other increment square. Okay, so I have to find that this thing here equals this thing here, because alpha squared plus beta square, that sum occurs in the nth step, and this thing here occurs in the n minus 1th step. So the only trick is the following. I'm conditioning here on alpha square plus beta square. Beta is the increment between s and u, but the Brownian motion has the same distribution if it has an increment xu minus xs, or the negative thing of this, because I have a normal distribution for the increment and that's symmetric. And that means if I only condition on beta square, I can distinguish between the increment beta and the increment minus beta, which means I can split up two cases here with probability half. Either I stay with a plus or I go to the minus. So this is just the same, because from the condition here, I can distinguish between beta and minus beta. But now when I have this here, well, I have an alpha square, I have a beta square, I have plus 2 alpha beta, and I have minus 2 alpha beta, which go away here. And in the end, I just have alpha square plus beta square, conditional on alpha square plus beta square. Well, that's exactly alpha square plus beta square, which makes this thing here a backward martingale. So of course you have to make more bookkeeping for everything which can happen, but that's the essence of the calculation. And that's the last proof of this talk. The only thing I want to mention is, well, based on this thing here. So we have a quadratic variation, which means the variation is infinite. And if the variation is infinite, there is no way that the Brownian motion can have a differential path somewhere. So I claim I have this thing here. So this limit here does not exist for any t with probability 1. So it does not exist. Or the probability that it exists is 0. So the paths of Brownian motion, they're pretty rough. Yeah, what we already had in one of the lectures, I think, is that one way to see Brownian motion is that by time dt, you either go up by plus square root dt, or you go down by minus square root dt. And, well, I said this, and the square of square dt is of course dt, and when you add it up, you end up in t, always. No matter if you go plus or minus square root dt, because the square is always dt. But these things here, so square root of a small thing is much bigger than a small thing, because the square root function goes from 0 like this thing here, very steep. And for this reason, the increment here is pretty big. And it's so big such that you do not have a differential path. You have a continuous path, but no differential path in Brownian motion. Okay, that's it for today. And next time we will continue studying Brownian motion. See you then.